The opinions expressed on this radio station, its programs, and its website by the hosts, guests, and call-in listeners or chatters are solely the opinions of the original source who expressed them. They do not necessarily represent the opinions of Revolution Radio and FreedomSlips.com, its staff, or affiliates. You're listening to Revolution Radio, FreedomSlips.com, 100% listener-supported radio, and now we return you to your host.
Ladies and gentlemen, welcome back to another episode of Cosmic Catastrophe on actual Revolution Radio Revolution.radio.
Yay, they're back.
Yeah, I am your host, Diamond, from the Oppenheimer Ranch Project. Joining us today is my lovely partner and co-host, Leah Shaper.
Hello.
Welcome to the program. We got a great show. Late phase solar flares, some new research coming out, may explain why Elon Musk's satellites burned up in orbit a few years back.
Mm-hmm.
So we're going to be talking about that briefly. Then we're going to move on to some new research on submarine canyons and some of the largest underwater avalanches ever recorded. We'll go through the geology, break it all down, and come to some conclusions there. And we will finish up the second half of the show with historic hurricane data, which may surprise you. All right. Anything you want to say before we get started?
Nope.
Nice shirt.
Well, thank you. Should I show the rest of the shirt? It's a pretty great shirt.
Oh, yeah. That is nice.
Yeah, baby.
All right. Let me know when you can see the screen.
I can see the screen.
And it says late phase solar flares could be more dangerous for Earth's communication than thought, according to a new study. So first, we have to understand what they're talking about here for the layman. When you read through this, it's a bit confusing. When a solar flare happens, there's multiple parts. The initial blast sends a radio blackout to Earth. It hits us immediately, and it can be quite severe. We can go up to complete radio blackout because of how it disrupts the ionosphere. And then there's the second phase. This is the part that brings us the solar storm. So there's stuff coming behind it, and there's like an intermediate phase in between too.
Mm-hmm.
But they really didn't talk about that.
Yeah.
But what they're saying here is the ultraviolet radiation, the secondary part of the flare as it's coming to Earth, could be more impactful than ever thought before.
Sure.
Did you read the article?
Yeah. I read part of the paper as well. And I mean, what struck me about it is we've talked about, I'm echoing a little bit. Maybe you could turn your speaker. What struck me is that we've talked about how, you know, the longer that the effects of a solar flare go on, it seems the greater for propensity for variation in the sort of electricity going on in the atmosphere, right? Like that there's a pulsing that can happen that can impact electronics on Earth, and maybe this is a part of that equation.
Yeah, it says here in the article, while it's well known the first wave of a solar flare, a sudden burst of energy from the sun, can knock out GPS signals and trigger global radio blackouts, the secondary emissions are less studied. And in this study, it suggests that the later phase, known as the extreme ultraviolet phase, could be just as threatening to Earth's satellites with more energy over a long period of time. Now, this research is coming out of the Queen's University in Belfast. Probably not a very big university. I've never heard of it.
I'm not sure I have either. Maybe once.
So the new findings from the researchers at the Queen's University of Belfast reveal that the late phase of solar flares has a greater potential to disrupt Earth's communication systems than previously understood. Well, isn't that just wonderful news?
Yeah.
We are in a magnetic excursion with a weakening magnetic field and an angry sun at solar max, but it doesn't really matter. These flares, large solar flares, can come anytime, even at solar minimum.
And it's funny how we're like living on a precipice at all times, it seems, with our sun, really, right? Because really, an event like, let's say, the Carrington event or greater could happen at any moment, right? There's not exactly rhyme or reason to it, but what we do know for sure is, like you just said, we're much more susceptible to flares, the results of flares, simply because our magnetosphere is weak.
Yeah, and well, what are they going to do about it? The interesting thing is we're just like learning about the science of these solar flares. And the bad news is that even hardening the grid won't make a difference.
Right.
With a big
Right.
enough event, nothing will make a difference.
Right. Right.
The good news is that humans have survived these types of events every single time.
Yeah.
And
Yeah,
even the
well, I
larger
mean,
events that we talk about that may be as far as reflected in archaeology in the form of the plasma petroglyphs worldwide, those could be some of the Miyake events.
right. But the difference is always with this is the difference in our infrastructure and technology, right? The danger isn't so much the flare as it is that our way of living is completely dependent on this global infrastructure that is electronically based, wire based, satellite based, and all of those things are highly susceptible to these flares. So it's not the flares. The flares aren't the issue. It's our way of living that's a problem. And the fact that everybody is dependent upon that. You know, if we weren't dependent on that, it would be a non-issue for the most part.
Right. So in the event of a huge event, we're going to have radio blackout immediately and no communication. And then 12, 16 hours later, the rest of the flare will hit in the form of a geomagnetic storm. And that's when it will light up the planet. It will knock out the grid. And the worst part is we have such a thick infrastructure of transformers. It's going to light thousands of fires around the world.
Right.
And we're going to be burning on fire at the same time global unrest occurs, because in a matter of a few days, everyone's going to figure out what's happened.
Yeah. Yeah. We've been kind of locked into a special kind of inflexibility, you know, because of our dependence on the way that we live. It's the same as the thing that I've been saying for a long time. When we have large scale, let's say monoculture agriculture and climate, and there's a major climate shift, our ability to adjust is greatly hampered by the enormity of that system, that you can't just pick up and move it. It's not like having regional or local agriculture that you can kind of relocate or adjust to some degree. It's kind of the same issue. You know, we're locked into our infrastructure, which will be very much affected by a large enough solar flare, which will then cause major disruption, fires, etc.
Yeah, and a lot of people will die very rapidly.
Yeah.
So here is the paper. We'll leave you links if you watch the rebroadcast tonight on Magnetic Reversal News on YouTube at 8 p.m. Mountain Time. We'll leave you the paper, the full paper, The Influence of Different Phases of Solar Flare on Changes in the Total Electron Content in the Earth's Ionosphere. And I think some of this may explain the unexpected space weather causing the reentry of 38 Starlink satellites in February of 2022. And there is also a paper that we will link below that is the title of it.
Yeah. Well, the thing you would have to tease out here is the reentry, because these satellites are not meant to stay up there forever, right? They have a lifespan of like 5 years or something. So there is a natural process of but no, there's a scheduled plan of reentry essentially, but there was an incident with some of these satellites reentering early.
Exactly.
Yeah.
In fact, 38 of them in this case.
Yeah.
Which was just simply blamed on a coronal mass ejection causing a magnetic storm and unexpected timing.
At unexpected timing? When is there ever an expected timing for a CME? That's funny.
Well, they had a scheduled launch for these satellites to go into space, and they had to go by that. They didn't know that the exact moment it hit the atmosphere was when the geomagnetic storm occurred.
Oh, okay.
That is almost impossible to determine.
Right.
And it wasn't, as I remember, it wasn't predicted to do anything, just like not even G1, and it got to that level. So that's what made it bad.
Well, that's interesting too, because I think you and I have both noticed in the last few years that often the effects of some kind of flare and or CME is more than we expected. Which would suggest that's a function of our weakening magnetosphere.
Yeah, a small shift in the BZ over the last 24 hours sent us into geomagnetic storm.
I saw that.
Yeah. And so I took a look what happened during the May Mother's Day superstorm of this year. And in fact, Musk's Starlink satellites were disrupted by that superstorm.
Yeah, I think we even talked about that.
One of the reasons might be because it lasted for 2 days.
Right.
It was it like reverberated.
Yeah, I mean, this kind of gets back to what I was trying to say in the beginning of the show, that, you know, perhaps it's the delayed elements of a solar flare that paper explores that is really responsible for technological failures more often than the initial impact.
Yeah, I agree. And it will be seen in the future at some time how it unfolds based on the size of the event and what's going on. Mm-hmm. One interesting thing that I want to point out in this paper is that the worst effect is on the daylight side of the ionosphere. That's what they found in the conclusions. So it is the Earth, it is the daylight side where everyone's at work when the major failures will occur. So everyone will be watching it.
Right.
It's
Everybody
not like
will
we'll
be
be
awake
asleep
for it.
Yeah, we won't be asleep. We'll see it happen in real time, everyone.
Yeah.
Oh, that's pretty scary. All right, let's move on to the next topic. Pretty interesting topic. And this is coming out from this article published by the University of Liverpool. A study reveals the devastating power and colossal extent of a giant underwater avalanche. Now, first question is, what are we talking about? Well, an underwater avalanche, as far as geologists are concerned, we call them turbidites or turbidity currents when they're in action. The turbidite is the deposit that's left afterwards. Which you would imagine is first a very coarse layer during the initial phase of the gravity flow or the avalanche, and then smaller and smaller particles, they fine up during the sequence. Does that make sense?
Yeah.
Yeah. And here's a nice computer-generated picture of what those turbidity currents look like. Now, these are happening all the time at the edge of the continental shelf as it drops off into the abyssal plain. And this is happening for a number of reasons. You can have major storms that move over these regions, causing huge currents, which create instabilities on the slope here in the submarine canyons, or even the edge of the continental shelf, and you'll get landslides. In the submarine canyons, you're more prone to that because you have more surface area on both sides for landslides to occur. And then you got a nice chute to accelerate the flow out into the abyssal plain. Now, you know, in catastrophism, a lot of people like Doug Vogt, Ben Davidson use this to claim that the submarine canyons, the presence of them, is evidence of the oceans being completely drained, washing over the continents, and then forming these canyons. You've heard of that?
Not specifically, but that doesn't sound right to me. And that's partially based on some stuff that I read in this paper, but anyway.
Right. So the way that all this is happening and the way submarine canyons get formed, which then accentuate these flows by forming a channel and guiding them further and further out, like the one we're going to talk about. The submarine canyons form when sea level is hundreds of feet lower out here on the continental shelf. So these canyons are actually rivers. They need a fluvial point source. So they're major rivers that are flowing over this exposed continental shelf during ice ages. And then the ocean re-inundates all the way up, covering the canyon up, which was formed by a river, and now forms a pathway for turbidity currents to flow down.
Sure.
So that's the whole process. You don't need a submarine canyon to form these turbidity currents. As you can see here, they can just form by landslides on the shelf itself.
Right. Well, just like you would imagine terrestrial erosion, right? I mean, we see that all the time. That pattern is all over where we live, right?
Yeah. And so very similar, but it's different in an ocean setting because these are density flow currents, which are slower and different than on Earth, like on the surface.
Well, and also have a tremendous difference in volume as well.
Oh yeah, absolutely.
I mean,
Because
just for, go ahead.
some of the most voluminous landslide deposits are dozens or hundreds of times bigger than anything on the surface.
Yeah, so like just for comparison, like this paper starts talking about like, so if you're talking about a snow avalanche, the typical end volume compared to the initial failure of the the instability, the initial volume that of the instability that caused the avalanche in the first place, the end volume is typically between 4 and 10 times the original size. If you're talking about another kind of like terrestrial debris flow, it could be like 50 times the initial failure. But in a submarine system, it could be up to 50 times larger than the initial failure. So that's just an enormous volume of material that's falling out, just based on the different dynamics that the water involved will cause.
Yeah, and this is not a new phenomenon.
Mhm.
The most famous area that I studied submarine landslides or turbidites in Pennsylvania is in the Ordovician. So more than 430 million years ago, 480, I think these turbidites were. So turbidites have been happening for all of geologic time, as long as there's been oceans and giant cliffs.
Mm-hmm.
Now, here's a really good example of why these things are forming. The slope is insane off the edge of the continental shelf.
Mm-hmm.
So any perturbation to Earth is going to cause these things to slide. And what I mean by that is, let's say there's a major earthquake. You could get dozens of these slides happening at the same time.
Mm-hmm.
And they continue to happen again and again and again in the same channel.
Mm-hmm.
And I have a great, look at this. This is a great image where the black is the edge of the continental shelf.
Mm-hmm.
And it just shows you how steep and severe this is. And take a look at this channel here and how long the channel moves out.
Right.
So the black up here is 400 feet of depth, actually 200 or zero almost on the shelf. And down here in the abyssal plain, we're talking 2,800 feet. So almost a mile straight down.
Wow.
The same as the Grand Canyon, as if you're on the edge of it.
Sure.
And ironically, the Grand Canyon looks exactly like this.
Right.
On the edge.
Right.
Even the mesa back here looks exactly like this.
Well, that's what I was saying earlier, right? We live in a valley with these chossy mesas that show exactly that same pattern.
And so you don't need to drain the ocean to get any of this topography.
No, I don't see why you would.
Right. And it's been happening throughout all of geologic time, these turbidity currents.
Right. And it's not happening at like some, interval. Would be fairly consistent across Earth.
There's one happening right now. I guarantee it.
Right. Right.
So you can get cyclones, you can get tsunamis that trigger massive amounts of these, earthquakes, tidal shifts, anything. The Earth in some areas, the shoreline along the east coast of the US is rising in some areas. Mm-hmm. That type of isostatic rebound would cause more and more of these landslides to occur because you're moving the crust.
And it's underwater, right? I mean, there are water currents. That's going to shift things and cause instabilities alone.
So that's what we're talking about. And this paper finds a particularly huge one.
Yeah.
Do you have a good summation of the flow that we're looking at here at Agadir Canyon?
I'm looking for so, okay, this is saying basically that the maximum initial failure volume, so the amount of material that it initially started to collapse, was about 1.5 cubic kilometers. And the total ending deposit volume was about 162 cubic kilometers. So the collapse, the underwater avalanche alone moved like 160 cubic kilometers of material. It's like it's over 100 times of its initial volume. It's enormous. And then I think I recall saying that it extended like 200 kilometers, something like that.
The whole canyon we're looking at here is 450 kilometers long.
Oh, so that can't be right.
Well, what happens
Maybe
is
it was
that
200 beyond the end of the canyon.
could be that. That could be that. Because what we have in here, it looks just like a flat bottomed river valley that we would see on the surface.
No, clearly not.
But what's happening is when you get the landslides up here at elevation, they rapidly accelerate down slope here. And they gather momentum and they rip the whole surface with them. That's how they accumulate so much additional volume as they go.
Well, yeah, as to that, so it depending on where you are in the canyon, in some places it's impossible to determine the actual depth of material that was eroded out in this process. But where is this? High up on the canyon margins shows that in some places the erosion was 4 meters in depth. So that's a lot of material, especially over such a long stretch.
Oh, let me see. Any more pretty pictures in the paper? No.
There are some.
So they radiocarbon dated this.
Mm-hmm.
I can't find any dates here.
Maybe I can find it.
I think they were using the dating to correlate the stratigraphy as they were moving through the section.
Yeah.
So you have to determine if this is the same turbidity current as the initial one you looked at as you move down the canyon.
Right. Right.
Yeah.
Yeah.
How does this submarine flow compare to others?
I don't have any numbers to tell you that.
Because I know there's a huge one we've talked about in the Mediterranean Sea. Do you remember that?
No, I don't.
Yeah, I think that might be the largest submarine landslide deposit ever found.
In the Mediterranean?
Yeah.
That's interesting.
Triggered by like a Santorini eruption.
Right.
So big volcanic, that's another thing we didn't mention. A large volcanic eruption, like in the Mediterranean, can cause this type of sloughing.
I sort of recall talking about stuff like this in relation to Cascadia as well.
There is no shelf per se on the Pacific. You need a passive margin, which we have here on the Atlantic. It's a subduction zone.
Yeah.
So they don't have the right topography to really get those submarine canyons, but we could pull, all we have to do is pull up
Google Earth.
And are you noticing that it seems like Skype is glitching a little?
No, I'm not experiencing that.
So
although I did have some other sort of malfunctions earlier, but not right now.
Here we are on the Googler. And anywhere you can see where there's this, I've got clouds now.
Yeah.
Where you can see this rapid change from light blue to dark blue. This is where these submarine landslides are going to occur.
Yeah.
And so there is a slight drop off here, but it's not like the continental shelf. And you do have some nice submarine canyons here.
Yeah.
See that?
Yeah. Yeah.
And that's coming from, these are extensions of where the river once flowed that's coming through here and this river system here and here. Mm-hmm. So when sea level was lower, these were actually, this was land.
Yeah.
And then once it gets inundated, these channels get accentuated all the way out into the abyssal plain. So these aren't very, there's some nice ones up here in Cascadia. So the reason they're bigger up here in Cascadia, I wonder why. Because this is where the 8 and 9 magnitude earthquakes occur.
Yeah.
So you can get this massive growth of these canyons. Look at how big they are up here.
Yeah.
And that's from turbidity currents. And as you get further and further away from the major source of earthquakes, then there should be some big canyons down here where the San Andreas is. And sure enough, look.
Yeah.
And that is also probably from massive earthquakes.
Interesting.
Come over to the East Coast and you got the continental shelf. You can get these flows even in the Gulf of Mexico. Do you see how there's a shelf here?
Mm-hmm.
They're everywhere. All of
Mhm.
these are canyons.
Mhm.
All from turbidity currents, not from the ocean washing over anything.
Right.
And then here, massive canyons on the continental shelf that go way out.
Yeah.
Look at this. All the way out here, and this is the end of the debris.
Yeah.
Wow,
So
that is hundreds of miles.
right. Well, so one of the
Well, actually, we can measure. Let me measure. 20, 40. It's only 150 kilometers, so 70 miles long. That's pretty
that's
significant.
that's plenty. I mean, one of the things that is brought up here is that this, especially a large submarine and avalanche is going to present potentially dangers to, like, let's say, internet cables, undersea internet cables, things like that. Oh, that's pretty severe.
All the way out into the center of the abyssal plain. Look, it keeps going
Mm-hmm.
and ends. The last lobe is here. So this is like the edge of the biggest landslide deposit right there.
Mm-hmm.
And this one, 80, 160, 300 kilometers. That's a 150-mile long canyon.
Yeah. Well, let's look at the one off the coast of Africa that this paper talks about,
Okay.
which is
I'm all
off the coast of West Africa.
Where at?
I'm not sure. Let's see.
In Chile, in Chad. I'm not even in Africa. I'm in South America.
What? Being on the right continent might help. Congo Canyon, but of course
Okay,
that's
all
not
we
going to
need
be labeled because it's offshore.
Oh, it's going to be so obvious wherever the Congo
It
is.
should be.
Where's the Congo? There's Congo. There it is.
Is that it? Yeah.
It's the only one
Yeah.
off the Congo River. But look, it's blurred for this
Huh.
video.
Oh, how inconvenient.
Yeah. So there's
Well,
the Congo
that
Canyon.
canyon is interesting too because it appears to get wider as it goes along. And it is directly coming out of the mouth of a river.
The Congo River. And so during the Holocene, this would have been land out here.
Yeah.
And this light blue is the old shoreline.
Mm-hmm.
So that's kind of interesting that we can't get resolution on that. But we can in the paper. All right, so that's the general synopsis on the submarine canyons. They're everywhere. And this is a particularly well-studied one. The problem is that there's not a lot of studies on these submarine canyons.
Yeah.
Did you have any conclusions or follow-up?
No, I was just going to say, if you went back to Google Earth, though, you could look directly for Agadir on the coast of Africa, and that would give you exactly that canyon. But
And maybe maps will give us a better picture too.
yeah, it's Agadir.
Hey, what?
It's Agadir. Go. Yeah.
That's what I wrote.
Oh, I thought you had a J in there.
Nope.
So there's
Yeah, they're not going to
Agadir.
give us anything.
No.
But it is right. Is it on the Congo River?
I can't tell from the map that I'm looking at because it's too small.
No, that's up in Morocco.
Okay.
Agadir is in Morocco.
Okay, so it's not off the Congo River. It's here.
Okay, here we come. Ladies and gentlemen listening on the radio, we are now looking at Google Earth. And we're going to wrap it around here and come up to Morocco.
Bear in mind, it's not like the entire ocean floor has been surveyed for these submarine avalanches. This is just one that was accessible and easy, relatively easy to study.
Yeah, but all the ocean up in Morocco is all blurred.
Yeah.
So we're not going
Bummer.
to see anything. Yeah, I wonder why there's good data everywhere else, but like up in here.
Huh.
Well, the same reason they haven't studied submarine canyons.
Right. Right. Yeah.
So the paper is extreme erosion and bulking, and that means getting bigger. I guess that's the way they call it. As the landslide increases, it's bulking.
Yeah.
In a giant submarine gravity flow. And that paper just came out 10 days ago.
Oh, is it
So
that recent? I didn't even look. Oh, yeah, look at that. Yeah.
We're on top of it.
Yeah, we are.
All right. The final discussion, the second half, is going to be about some historic hurricane data that this team found some interesting things that were unexpected. All we hear about in the news is climate change this, climate change that, increase hurricanes, and blah, blah, blah. But the fact is, this year they predicted 26 named hurricanes, and I think we're on F.
Mm-hmm.
We just had Ernesto.
Right.
So where are the 20 other hurricanes?
Well, also that claim of increased hurricanes is based on a very limited data set. I mean, what's important about this paper is that it's essentially trying to reconstruct hurricanes of the past, of centuries ago. We don't have that data. So when people say things like, oh, there's more hurricanes, we're literally looking back to like what? I don't know, 1800 maybe?
Yeah, well, probably that's all we have. And there wasn't that many people here. So if there's nobody in Florida when the first colonies are here, they're not going to see any hurricanes.
Right. Well, so right. So it's also dependent on what people recorded, what kind of instrumentation they were using, if any, like, again, very limited data.
Well, and we also know from the work of Ryan Maui that there's no increasing in hurricane force or frequency in the last 50 years.
Right. Right.
And what we can see from our very own eyes is it seems like they're decreasing now.
It's weird, though, that people really have the perception that there's increasing number of storms and increasing severity of storms just based on what is being said in the media. I had a conversation with a friend of mine a couple of months ago, generally talking about the lie that is human-induced climate change. And the objection was, but what about the increase in the number of storms and their severity? And I said, well, that data that's not what the data shows. But there's great skepticism. People are very prone to believing that because every time there's a big hurricane that causes a lot of damage, I think that it sticks in your brain. I think it has like an emotional component that really sticks with people. But you have to remember that and in fact, there's some old psychological experiments proving this, that emotional events are often misremembered. There's a really famous experiment that was done regarding the Challenger explosion in the 80s. So they took a group of people who, experienced the Challenger explosion in the sense that, they heard about it on the news and witnessed it and whatever. And then they asked the same group of people, I think it was 10, must have been 10, it had to have been 10 years later, the same question. So right after the Challenger explosion, they said, where were you? How did you find out? It was kind of like all the who, what, where, why, how questions about the circumstances of learning about the Challenger explosion. They asked all the same questions 10 years later. And what they found was that all of the elements in the memory were like mixed up. So, like maybe one person in their first report said that they learned about it on the television, on the news, and their friend John was sitting right next to them crying. And then 10 years later, the memory is, John is telling them about it and he heard it on the news or something like that. So all of the elements. So it's like you have to, it just shows, it goes to show that you can really take advantage of how people remember information, especially when it comes to emotional events. And I think that a lot of hurricanes and such are emotional events that really stick in people's minds. And so when you tell them that the severity and the number of storms hasn't increased, they don't believe you. Even looking at the data, they won't believe you because they'll be like, but my experience is this. And it's like, well,
yeah,
your
I
memory
heard it
isn't
on the
necessarily
news.
accurate. Huh?
I heard it on the news. They lied to me. They told me that things are increasing and it's my fault. I heard that 800 times. And there's
Right.
nothing you can say to make me unbelieve it.
Right. Well, so again, this is precisely why the the manner in which the global climate change hoax has been perpetrated works, because you're telling people that they themselves are responsible. It's their fault. And so again, you're inducing an emotional response, and so it really sticks with people.
That's the sad state of the world, unfortunately.
Yeah.
So now that we know that there is no increase in hurricanes, you would be, well, inclined, especially if you were a global warmist, and I told you this, you would have no explanation for it. That there was a period from 650 to 1250 that the Gulf of Mexico saw unprecedented amounts of tropical activity. And this happens to coincide with very cold times on Earth, a time called the Maunder Minimum, with low solar activity,
Yeah.
cold temperatures, and yet increased hurricanes.
Interesting.
So the study is very thorough and at the same time vague in the sense of how they approached it. They went into protected inland areas that are coastal, like on the opposite side of barrier islands, like estuaries and bays, to find unique storm deposits. In order for sand to get from the ocean over these into these bays, you need huge storm surges. And usually those are caused by hurricanes. They could be caused by something else, but typically they're hurricanes. So this is where the vagarities come in. We don't know if they're hurricanes. We weren't there. But the only way to get shells and sand to these places is a big storm and a huge surge.
Well, it's not totally vague in the sense that, for each particular place that they looked at, they kind of looked at like, what is the threshold, let's say, for getting this deposit in this area? And so that then enabled them to say, okay, the surge had to be this big. So that did kind of allow them to gradiate like how big storms were. And that's what they're looking for. They're looking for significant storms.
Right. And some of this could be due to what we just looked at. Submarine canyons here in the Gulf of Mexico, I pointed out all over here, have historically created tsunamis when they move. So the landslide happens, the ocean bulges from the effect, and a small tsunami occurs, and that would look just like a hurricane deposit.
Right.
So they really can't tell what they're looking at. But what the evidence they found was overwhelming in the sense that, let's get to some of these graphs.
Well, in the sense that there's a pattern in time.
Yeah, there is a millennial scale pattern.
And I don't think you could say, kind of like what we were saying earlier, as far as we know, there's no pattern, there's no time pattern for submarine avalanches. Like it could be happening at any time. Like given that it can be triggered by not much, there shouldn't really be a time pattern. Whereas for storms, there very well may be simply because there are patterns in climate over time.
Exactly.
God, I keep saying time. I sound like Kamala Harris.
Time.
The significance of time.
All right, so you can see in this chart multiple data sets. They go from 0 to 2000. And down here, it's weird. They reverse it, 0 to 2000.
Oh, that's so annoying. I didn't even notice that earlier.
But there is a huge spike in activity between 600 and about 1250 or 1300. And it's different in different regions, but there is a massive spike in hurricanes or major storm activity during this time, which coincides with the Maunder Minimum. Where did I get that graph? Oh, there it is. So let me move you. All right. So here is 600 is right at the beginning of the European Dark Age, one of the coldest times on Earth. And there is an increase in hurricanes during this time. And the increase goes all the way up to the Great Famine and the Black Death. So it does encompass the medieval warm period as well, but also very cold periods as well, which
That's interesting.
Doesn't make sense to what they're telling us. They're telling us that it's the hotter it gets, the increased sea surface temperature, more bigger storms.
Mhm.
Well, how could you get increased sea surface temperatures during the European Dark Age? That doesn't make any sense.
Well, I mean, if you actually read this paper, they are saying, look, there are all of these variables. It's not just sea surface temperature.
Yeah. And so the conclusion here is very interesting. Differences in hurricane patterns between the Gulf of Mexico and the Atlantic coast in the United States suggest factors influencing local cyclogenesis or storm maintenance, but also may play a role in late Holocene hurricane activity. And what they go on to conclude is that there is an area everyone knows that these hurricanes form off the coast of Africa. So this is the Atlantic Hurricane Formation Zone. That's where they form. So that is the place that needs to get warm.
Yeah.
North America could get cold, let's say. But
right.
if the sea surface off the coast of Africa is still warm, it's going to generate hurricanes and send them towards us. And even if the temperature is a degree C colder, it's still summer. During hurricane season, the Gulf of Mexico is shallow, and it always gets warm in the summer. Even in the middle of an ice age, I bet the Gulf of Mexico gets warm in summer.
Yeah.
And so what's happening is this is what it is right here. That's the loop current. Enhanced hurricane activity in the Gulf of Mexico coincided with warmer sea surface temperatures in the MDR. That's the region off the coast of Africa and within the Gulf of Mexico. So as long as you have those two things happening, you can form the hurricane and you've got warm water to sustain it. You're going to get increased hurricanes.
Yeah.
And so there's evidence for a more northerly.
That's intertropical convergence zone.
Convergence zone, right. So, and a stronger loop current at the multi-centennial timescale. So what this reveals is that there's these climate systems within systems that aren't all linear. Like this is a linear thinking of global warming. Everything's going up in one direction. It's all going to increase and get worse. But based on this study, it's absolutely far more complex than anyone could imagine.
Yeah, when you think about it, all of the concepts that have been suggested for anthropogenic global warming are wildly simplistic, and there's so many variables in this equation, not just for storms, but for anything climate related. So I mean, that again makes sense though, because if your goal is really to control people, then you're going to utilize a narrative that's very simple that people can easily digest.
Yeah, and what this paper also concludes is totally against anthropogenic global warming.
Yeah.
It says the reduction in landfalling hurricanes circa 1200 CE, that means for the last 750 years, we have had less hurricanes, even though they're telling us we've had more. Guess what the reason is for less hurricanes now? Cooler sea surface temperatures.
Right.
And they're saying it's the hottest ever, the season and everything.
Yeah.
During the European Dark Age, we had hotter sea surface temperatures. Let that sink in.
I appreciate both that. Not as far as I saw, I didn't see one mention of anthropogenic global warming in this paper at all. And I also really appreciate that it opens with a statement that I think is important, right? It says, tropical cyclones are a serious threat for densely populated coastal communities, particularly the Florida Panhandle, where growing concentrations of people and properties have resulted in a steady increase in damage from hurricane landfalls. In other words, the damage is caused by more people living there rather than some imaginary increase in the number and severity of hurricanes.
Right. And if you haven't been to Florida, the number of people living in inappropriate areas is insane. There are tens of thousands, probably over 1 million homes, literally built on tidal rivers. And anytime a hurricane comes, they all get inundated. They all get insurance claims. They all fix them. And 3 years later, everyone forgot what happened.
Right. And then it happens all over
bizarre.
again.
It's so bizarre.
It's like playing Russian roulette. Like, it's bound to happen eventually. You just don't know when exactly.
Well, and with the shaky nature of the globalist takeover and the collapse of the insurance industry, many of these areas in Florida that get hit, at some point it would be illegal to rebuild. There will be no insurance, and there's going to be just abandoned ghost towns on the edge of these estuaries. The future is not, I don't see it getting, I don't see any bright lights in the future. Do you?
Well, there is a bright light, but I'm not going to say it because it's going to sound terrible. So,
right. So, what I find interesting is that here's another interesting tidbit that they didn't go into: the sun. So, what we know is during the Maunder minimum, the sun went completely dead, right?
And we don't mean that it turned off, by the way.
No, so
I just want to say that. I get really frustrated when people say that the sun turns off. It doesn't turn off.
Just low sunspot numbers.
Yes.
And that coincides with the end of that hurricane activity. So once we went to this really cold, low solar activity, it may have cooled the oceans, and they're still cool today. Because the conclusion is the reason for the last 700 years, there hasn't been a large number of hurricanes, landfalls in the Gulf of Mexico and the Caribbean is because the sea surface temperatures in that, what do they call it? Where the hurricanes begin off the coast of Africa. They've got a fancy acronym.
Yeah, I don't remember what it is.
But that is the region where the sea surface temperatures have been cold for the last 7 centuries, colder than it was before, which is leading to much less hurricanes.
Interesting.
And maybe hurricanes may increase in the future if that area, in fact, warms up, and the ocean is warming.
Right.
So there may be a time in the future that is very scary. If that area heats up, just look at the graph. I mean, this is far more frequent than this.
Yeah.
And we think that this is scary.
Right. I was about to say, so, when
look at this activity right here for 600 years compared to this flat line.
Yeah. Well, what else is interesting too about this is that these areas in this graph here, they're relatively close to each other, but you can see a difference in pattern between them. So it's like, if we understood this pattern fully, we would really be able to predict where most storms are going to land in a given time period. And that's very specific because those are pretty close to each other.
Well, and if you look at the patterns here.
Yeah.
It's not loading everything. What's going on? Okay, there it is. Yeah, these storms change direction rapidly. There's not a lot of similarities. Look at this path
but
here.
you see how where
1985.
is,
look at this, does a loop-de-loop and then goes the opposite direction.
Right. But I mean, looking at all of these storms and the proximity to that starred location, which I think is it's one of those locations listed there. I mean, it's interesting.
What is underneath of there drawing all the storms to the star?
Right. Right.
Well, there's far more storms than this, but the area in question that they were studying, they only wanted storms that came near there. So that's what's going on there.
Yeah.
All right. So the future looks great right now. We're not living in a world 1,000 years ago where there was 5 times as many hurricanes hitting the Gulf of Mexico, which is a good thing. But at that time, the Native Americans were all over there.
Yeah.
That must have been crazy. I mean, I've been out to Mound Key in Estero Bay. They were living in the middle of a bay on a shell island.
Right.
Like riding out a hurricane there would have been brutal.
Well, but were they there in this time frame that we're talking about, 650 to 1250 would be the question.
Yeah, that's
maybe
when
they weren't there in that time
native
frame.
populations across North America were booming. That's the exact time. That's the Pueblo time, the cliff dwellers, the Anasazi.
Right.
700 to 1300.
Bear in mind that a lot of these people were far more flexible and adaptable than we were, like in the sense of not necessarily being married to one location, migrating seasonally, So if you're living like that, it's going to be a lot easier to respond and get out of a danger zone when necessary. And surely there was also a hurricane season.
Yeah. That
Yeah.
has never shifted.
Yeah.
The peak is the peak is September 10th.
Yeah.
Then it falls off a cliff.
Which is about to happen. And we've hardly had much in the way of hurricanes this year.
There are 3 tropical disturbances currently on the map, and there have been none. And disturbance number 2 appears to have the greatest chance of making landfall currently on Texas in about 10 days, maybe 13 days.
Mhm.
And the model last night showed it as Cat 3 or 4. So we could see something interesting here, but it's so far out. I could probably just pull it up. We'll see where we're at on the newest run here. And it's so hard to manage your face.
What do you mean?
You're always in the
Oh,
way of what the screen is. I got to move you around.
It's not my fault.
No. So this GFS model has no hurricane on it. That's good news. See that little thing coming through there on the bottom?
Yeah.
That would be the system breaking up and hitting the Yucatan.
Yeah. I mean, if there is a hurricane, they're going to have to take, let's say there's one hurricane this season, they're going to have to take that and blow it up way out of proportion to continue the narrative,
Oh, yeah. So scary. It's all your fault. But if there isn't any, it'll be silence.
Yeah. Well, they'll just talk about some other, scary global warming something or other. So I wonder too if around 1800, what was going on there, just simply because what was that, the Dalton minimum?
Yeah, so this is the Dalton. This is the Centennial minimum.
Yeah.
And the modern minimum just began. Cycle 24 would be the same as 12 or 14 here.
Yeah.
It's not on here. Yeah. Cycle 25 is now at about 130 smoothed. So like a cycle 20. So we have 2 small cycles here that are part of the modern minimum.
Yeah.
But all 3 of those minimums pale in comparison to the Maunder, if in fact this sunspot data is slightly accurate.
Right.
It could be that just no one was looking at the sun.
Right.
That the data was low. See how these are low data spots here?
Yeah. Yeah.
But they were, they have spikes here.
Yeah.
All throughout the Maunder.
Yeah.
There's 5 sunspots, 4, 3. Maybe they just weren't looking at it.
It's possible.
Yeah, because what we have is different data sets. The purple line is Hoyt yearly GSSN, which goes from 1600 to 1750. I haven't looked into that data set. And we got 3 data sets here laid over each other.
Well, and then there's also some differences in how we count sunspots these days, correct?
Yeah, we talked to Willie Soon about that, and he has a whole paper about it.
Yeah. But also, like you said earlier, right? It's quite possible that this is all the result of a lower sea surface temperature off the coast of Africa that has persisted.
Yeah, for several hundred years.
Yeah.
And maybe, there's so much to think about. If the AMOC shuts down, what other parts of the ocean get hot or cold? We don't know that. We've never been here. But the postulation is if the AMOC shuts down, it gets cold in Eastern Europe because there's no more warm water moving up to keep it warm. Just like the warm water keeps California perfect. Yeah. If the Pacific got cold, it would be terrible in California. Because they have a giant mountain range nearby.
Yeah. It's really ridiculous to think about what we were talking about a few minutes ago. How many variables are involved here? You've got the AMOC, you've got the ENSO cycle, mapping out how all of the sea surface temperatures around the globe are impacted by all of these things. You've got total solar irradiance. You've got albedo. There's so many things that go into that are the inputs into the Earth system.
We've got El Nino and La Nina, which has been going on for hundreds of millions of years.
Right. And yet we supposedly have it all figured out that, CO2 and greenhouse gases drive everything and the sun has nothing to do with it and neither does any of this. It's absurd.
Yeah, that a trace
It's totally
gas,
absurd.
yeah, 0.0% of the atmosphere, a trace gas that we contribute 4% to, has something to do with all of the data we just showed you.
Right. It's like, what? I mean, like I said earlier, it's really embarrassing, but it also makes sense from the perspective of a global agenda, because by providing this very simplistic idea, you create an idea that most people can digest and take on, and then feel terrible for existing.
Exactly.
It's tremendously diabolical.
And what's happening in Brazil and Europe with censorship, the arrest of Paval, and the
Pavel
shutdown
Durov.
of Twitter and Rumble in Brazil is
Yeah.
only the beginning.
Yeah. Coming to a country near you. Find us tonight.
Resist at all cost.
Find us tonight on Magnetic Reversal News at 8 p.m. Mountain Time on YouTube.
Listen to Revolution Radio at freedomslips.com, and we'll be right back after this message.